we propose a transformation-based approach to obtain cross-lingual contextualized embeddings from pre-trained BERT models. Then, we demonstrate the effectiveness of our method on zero-shot cross-lingual dependency parsing task. To begin with, I'd like to introduce the task of zero-shot cross-lingual dependency parsing. As shown in the lower graph, the goal of such task is to directly apply parsing models trained on the source language to the target language. And the predicting procedure is often achieved with the help of cross-lingual embedding. One of the most promising directions for cross-lingual dependency parsing is to bridge the gap of lexical features. At early ages, the lexicalized models only use part-of-speech texts that are shared across languages as input features. Later on, previous works have shown that cross-lingual word embeddings obtained from pre-trained static ones can significantly improve the performance. Recently, contextualized word embeddings obtained from pre-trained language models such as ELMO and BERT have achieved amazing success in many monolingual NLP tasks, which has inspired us to extend their potential to cross-lingual scenarios. In this work, we have demonstrated that such contextualized cross-lingual word embeddings can further improve the performance of cross-lingual parsing. Several recent works have been proposed to learn contextualized cross-lingual embeddings by training cross-lingual language models from scratch with parallel data as supervision, which we will refer to as online learning methods. Compared to these methods, our proposed cross-lingual BERT transformation approach, or CLBT for short, is an offline method, since it exploits publicly available pre-trained monolingual BERT models and learns a linear transformation to project the BERT embeddings to a shared semantic space. In such way, our CLBT approach requires much fewer training data computing resources as well as less training time than previous online learning ones. Let's see an illustration of our CLBT method. Here, the contextualized embeddings of Spanish word canal is transformed to the corresponding semantic space in English. Embeddings in both languages have two different meanings, namely a TV station, the orange ones, and a passage of water, the green ones. Since our method utilizes the semantic equivalence in the contextual word alignments, it is word sense preserving. As shown in the graph, embeddings with the same meaning are closer to each other after the transformation. Then, I will introduce the training procedure of our method. Different from conventional static cross-lingual embedding learning, which requires supervision at word type level, such as cross-lingual dictionaries. To learn contextualized cross-lingual embeddings, we need word token level or context level supervision. Therefore, we use parallel corpus for training and obtain contextual word alignments, namely aligned word pairs with their contexts, using the unsupervised fast align toolkit. While training, we aim to find a linear transformation W, which is applied to the embeddings X in target languages to approximate the corresponding embeddings Y in the source language. Prior work has shown that an analytical solution of such a problem can be obtained with singular value decomposition. Besides, we also tried an approximate solution with gradient descent to save memory required in training procedure. For the experiment, we employed the bi-affine graph-based parser of Doze and mining and replaced the pre-trained static embeddings with cross-lingual ones while predicting on the target languages. We have conducted experiments on 18 languages from Universal Dependency Tree Banks version 2.2, and we choose English as the source language and all others as targets. We compare our method with 3 strong baselines. The first is the previous state-of-the-art on this dataset, which used conventional offline static cross-lingual embeddings. The second is the multilingual BERT, which is trained on multilingual corpora but without explicit cross-lingual supervision. And the third is XLM, an online learning method which learns contextualized cross-lingual embeddings from scratch. This page compares the results of our CLBT methods to the fast text SVD and multilingual BERT methods. The y-axis is the labeled attachment score in the dependency parsing task. It is obvious that our methods outperform the 2 baselines in almost all languages, and overall, from the averaged LAS shown in the upper right, we can say that CLBT outperforms the 2 baselines by a substantial margin. Then, we compare CLBT with XLM, a powerful online learning method. We employ the model they have released and compare with them in the 4 overlapped languages both works have researched on. The left graph shows that CLBT achieves a comparable results to the XLM on the 4 languages, while the table on the right shows that our method requires much less training data with such comparable results. Besides the experiments, we have also conducted some interesting analyses on our method. Here, we visualize the contextualized embeddings of the English word nature and its Spanish translation in different contexts before and after the transformation. Each point in the graph represents a contextualized embedding in different contexts, and they are colored by word sense. The blue points in both languages share the same meaning, namely the physical word, while the red ones mean the inherent features. As we expected, the embeddings of Spanish words after transformation are closer to those with similar meanings from English, which further demonstrates that our method is word sense preserving. Then, we further analyzed the effect of training data size on the performance of zero-shot cross-lingual parsing with the CLBT method. As shown in the graph, for most of the languages, the best performance is achieved with only 5,000 paired sentences. In our experiments, we used 10,000 sentences for each language pair. And it is also worth noting that for most Germanic and Romance languages, such as German, Danish, French, and Italian, a rather small training set of merely 100 sentences is capable of achieving comparative results. Lastly, our codes and models are available at the GitHub. Since it is not fine-tuned on parsing task, we assume that it could be applied to any cross-lingual task. So please feel free to test it on your own task. Thanks for your listening. Hello everyone. I'm glad to...
we have one of the co-authors of this paper here, so perhaps one question? So they can be answered. Okay. Yes, please.
Hi, thanks for a great talk. I mean, a great work, sorry. Did you compare to using, you did the contextual alignment, aligning token level word pairs, right? Did you compare to doing alignment of the average embedding for a word, like a NACL paper earlier this year. I can't remember.
I think so. No. Yeah.
Okay, thanks.
Okay.
Another question? Okay, then thanks, Wanxiang.